What are cosmic strings, and what do they have to do with string theory? You've probably heard of string theory before. It is a framework that aims to solve all physical problems, including the quantization of gravity, and ultimately unify the four fundamental forces into a single theory. It is also known as the theory of everything. Unlike particle physics based on quantum mechanics, the defining feature of string theory is that it no longer treats all fundamental particles as dimensionless point particles, but instead as one-dimensional strings. Those fundamental particles are simply different modes of vibration and motion of these strings. As a theory discovered ahead of its time, string theory currently lacks experimental verification, and the theory itself is still quite rough. In its present form, string theory is essentially a mathematically stitched-together prototype, rather than a fully developed physical theory. Even so, string theory is still regarded as the most promising candidate for a theory of everything. As a result, many researchers hope to use it to address problems that modern physics has not yet been able to solve, including many questions in cosmology. However, when it comes to cosmic strings, they initially had no direct connection to string theory. Calling them strings at the time was more of a coincidence. Back in the 1970s, when string theory had not yet taken shape, the British physicist Tom Kibble proposed a completely unheard of cosmic structure. This structure would continue to grow longer over time, and today it might even be comparable in size to the radius of the observable universe. These gigantic objects are made of neither ordinary matter nor dark matter, yet because they can radiate gravitational waves, they are capable of influencing both, and may even play a role in shaping the evolution of the entire universe. At the time, including Tom himself, people did not believe that such objects would ever be found in the universe. His idea was more of a purely theoretical speculation. Tom's field of expertise was quantum field theory. He frequently studied phase transitions, topological defects, symmetry breaking, and related topics, and he was also deeply interested in cosmology, especially the early universe. He realized that existing gauge theories were already able to explain many phenomena. If these theories were correct, then, according to theoretical expectations, spontaneous symmetry breaking in the early universe would lead to phase transitions in the vacuum. A phase transition is simply the process by which matter changes from one state to another. For example, when the temperature is low enough, water transitions from a liquid into solid ice. Similarly, the state of space itself can also change, which corresponds to a vacuum phase transition. When a vacuum undergoes a phase transition, it usually means that the lowest energy level of space has changed. This can alter fundamental particle properties such as mass and charge, and also affect how basic interactions like gravity and electromagnetism behave, potentially even changing physical laws themselves. Vacuum phase transitions are not perfect. During the transition process, various topological defects may form, just as cracks can appear when water freezes into ice. These imperfections in vacuum phase transitions can give rise to special phenomena, such as magnetic monopoles and the cosmic strings we are discussing today. Cosmic strings are one-dimensional, line-like objects. Their diameter is almost comparable to that of a proton, yet their length can be stretched to enormous scales, reaching astronomical or even cosmological dimensions. As a whole, a cosmic string is unimaginably long, yet unimaginably thin. Thin as it is, thinner than silk, really. It contains an astonishing amount of energy, with an extraordinary energy density. The equivalent mass of just 1 kilometer of a cosmic string can exceed the mass of the entire Earth. Seen this way, it is not impossible for a cosmic string spanning a light year to generate gravitational waves that could be detected. From the time Tom first predicted the existence of cosmic strings to today, nearly half a century has passed. During this time, the concept of cosmic strings has attracted increasing attention from physicists, especially string theorists. Unlike earlier derivations based on quantum field theory, string theorists started directly from superstring theory, and showed that, in certain scenarios, the fundamental strings, or F-strings, of string theory can be interpreted as cosmic strings. Fundamental strings refer to the open strings and closed strings commonly discussed in string theory. D-strings, on the other hand, are related to branes in string theory. The D refers to D branes that fix the endpoints of open strings, while the 1 indicates a one-dimensional object. You might say, so it really is mystical, this just keeps getting more abstract. So do cosmic strings actually exist? Although in the early days scientists did not believe we would ever find cosmic strings in the universe, after decades of progress, there have indeed been some suspected indirect pieces of evidence in certain areas. One example is gravitational lensing. Gravitational lensing caused by cosmic strings often has some distinctive features. If a cosmic string is perfectly straight, it should theoretically produce two symmetric, undistorted images. For example, in 1979 astronomers discovered a peculiar pair of quasars. In 2003, astronomers also found two galaxies that looked completely identical and were extremely close to each other. These phenomena were once thought to be lensing images, caused by the gravitational effects of a foreground cosmic string. Unfortunately, these possibilities were later ruled out. They turned out to be either gravitational lensing caused by foreground galaxies or galaxy clusters, or simply two very similar galaxies. Later, physicists suggested that cosmic strings do not necessarily have to be straight, they could also be curved. In such cases, the images produced would be asymmetric, yet still different from lensing images caused by ordinary celestial objects. However, so far we have not found any cases that clearly match these characteristics. Beyond gravitational lensing, cosmic strings have also attracted attention for their potential role in explaining anisotropies in the cosmic microwave background. In theory, background radiation should be extremely uniform, but in reality, it is not. Scientists believe that the gravitational effects of cosmic strings could influence the large-scale clustering of matter in the universe. This unevenness in the background radiation may be a result of such influences. In addition to appearing in the cosmic microwave background, these effects could also impact the later distribution of galaxies and galaxy clusters. However, based on high-precision measurements of background radiation by the Planck satellite, scientists have calculated that, even if cosmic strings do exist, under current conditions, their contribution to background radiation anisotropies is less than 10%. Their influence on the distribution of galaxies and galaxy clusters also appears to be quite limited. At present, the strongest support for cosmic strings likely comes from a major development in recent years, the discovery of nanohertz gravitational waves. Using pulsar timing arrays, scientists have found that our universe is permeated with extremely low-frequency gravitational waves, with wavelengths that can reach light-year scales. Scientists believe that these gravitational waves may originate from mergers of supermassive black holes or primordial black holes, or from certain phenomena in the early universe, such as cosmic strings. All of this points to one key idea. Compared with the strings of string theory, cosmic strings are more macroscopic in nature, and therefore easier to detect. They are not as purely mathematical as string theory, and can be explored more directly from a physical perspective. It is important to note that, although there are now some theoretical ideas and observational efforts related to cosmic strings, these remain very preliminary attempts. For humanity, the universe still holds countless unsolved mysteries, but humanity's quest to explore the cosmos will never come to a stop.